So good morning all, welcome to Sakala Vidya YouTube channel. Okay, good morning. So welcome to functions part 2 class. This is Eamcet class. But one more thing I would like to discuss with you. Evening 4:30 to 5:30 class is not Eamcet class, that is actually foundation classes for JEE mains. So in that I will discuss even derivations and etc. Please, those who are not interested actually from, so don't come to those classes, but you just recommend to the juniors classes, for your juniors only. The classes are, those classes are meant for those who are pursuing next year second year students, outgoing second year batch students. Please do remember. So that is not MSET classes. MSET classes will be conducted only in the morning classes. So that means in 9:30 to 11:20 are like that. So you might have understood. Yesterday, the few viewers actually of MSET have disturbed me a lot. But today onwards, if anybody disturbs, you will be kept hide itself only. And moreover, and one more instruction, today if anybody chat unnecessarily, they will be removed from our group. So please remember these conditions, otherwise you can leave, no problem. Thank you. Functions part 2. This is MSET. Okay, so yesterday we have discussed up to one-to-one functions, and next many-to-one also. In many-to-one, you remember one important point, that note down. Important point. If n of a less than or equal to n of b, then the number of many to one functions from a to b is n of b to the power of n of a minus n of b p n of a. That means total number of functions minus number of one-to-one functions. That gives us the number of many-to-one functions. So let me discuss one example now. One example. Let a equals to 2, 3, b equals to a1, a2, a3, a4. Here clearly n of a is less than n of b. Then number of many to one functions from a to b. This is the question. Now here solution, first n of a equals to 2, n of b equal to 4. Since n of a less than n of b, one-to-one functions are not defined. So that means number of many to one functions. Many to one functions. Many to one functions is equal to n of b to the power of n of a minus n of b Pn of a. n of b equals to how much? 4. This is 4 square minus this will be 4p2. So 4p2 is equal to how much? 4p2 equals to 4 factorial by 2 factorial. This will be 4 into 3 into 2 factorial upon 2 factorial. 2 factorial cancel, 12. This is 16 minus 12. So answer is 4. Answer is 4. Okay, next we have onto or surjection. Onto or surjection. Onto or surjection. A function f maps a to b. A function f maps a to b is said to be onto or surjection. Surjection if every element of B is the image of some element of A under map F. So that means no element is left in the codomain. That means no element is left in the codomain. For example, if it is not onto function, then it is called actually into function. Here I done a function f maps a to b is an into function if it is not an onto function. You remember this one also, into function. Okay, onto function means we can say that like this also. The range of the function is equal to the its codomain. So that means range of the function here codomain is B. For example, f of A is equal to B, then f maps A to B is called uh, surjection also. So like this also we can write f of A equals to B. That implies f maps A to B is onto function. This also we can remember. Right. So let us consider the example. Let us consider examples. See, A, say B. Here 1, 2, 3, 4. Next 2, 3. 1 is mapped with 2. 2 is mapped with 2. 3 is mapped with 3. 4 is mapped with 3. Okay. This is function f, for example. Here actually see what is the range of this function 2 comma 3. What is the codomain? B. So that's why here range equal to codomain, then this f maps A to B is onto. Here no element is left in codomain. Consider another example now. For example like this. Say A, this B. For example 2 comma 3 A, B, C. 2 is mapped with A, 3 is mapped with C. Now actually here range is A comma C. A comma C is the subset of B. Now it is not onto function, it is said to be into function now. For example, say this is H maps A to B is not onto function, is not onto. Now important point. Important point. Important point. If A and B are any two finite sets having m and n elements respectively, where 1 less than or equal to n less than or equal to m, then the number of onto functions onto functions from A to B equals to sigma r is equal to 1 to n minus 1 to the power of n minus r ncr r to the power of m. This equals to expansion will be like this: nc0 n to the power of m minus nc1 n minus 1 to the power of m plus nc2 n minus 2 to the power of m minus nc3 n minus 3 to the power of m plus dash dash. So this is the formula to find out number of onto functions defined from A to B. Understood now? Next, the number of into functions which are not onto. Number of into functions. Number of into functions is equal to, we have nc1 n minus 1 to the power of m minus nc2 n minus 2 to the power of m plus nc3 n minus 3 whole to the power of m minus dash dash dash. So please note it down. It's very important. This concept is very important. And moreover, once again, actually, some new viewers are joined. So don't chat any personal FIs. Don't chat about the results also. So whatever results it may be, you need to discuss yourself itself only. Thank you. I will discuss the examples in the problems because still we need to discuss more in this one. Right. Next, test. How to find the given function is onto or not. Test. First point, find the range. Find the range of the function f. Second point, if the range of f equals to b, codomain, already told you, then f is onto, otherwise into, otherwise it is into. So this is the test we need to conduct. Vivek, Sunny, don't discuss all these things now. Okay. Right. Next now, bijective function. Bijective function. Bijective function. What is meant by the bijective function? A function f maps A to B is said to be bijective if f is both 1 to 1 and onto. That is called bijective function. It should be 1 to 1 as well as onto function. Then it is called bijective function. So now one example, let me write one example here. Only I will discuss examples, problems later. Don't worry. For example, say this is A, B, C, 1 comma 2 comma 3. A to 1, B to 2, C to 3. Say this is F. See, for example, here first you observe this. Distinct elements of A are associated with distinct elements of B. So it is 1 to 1. So now what is the range of this function? In test 1 comma 2 comma 3. What is its codomain? That is B. So that's why this range equal to codomain, this function is called both 1 to 1 as well as f maps A to B. F is 1 to 1 and onto. Therefore, f maps A to B is bijective, is a bijection. This is one of the examples. So now next point. Now important point, right? If A and B are any two finite sets having the same number of elements, say n, then the number of bijective functions from A to B equals to npn, that equal to n factorial. Because see, so now surjection means very simple, range equal to codomain, that's all. That's called surjection. Okay, here see, in this one, n of A equals to, here we can write like this also, n of A equals to n of B. Whenever n of A equal to n of B, then only bijective function is defined. Otherwise, bijective function shall not be defined. Understood now? This is called bijective function. This is bijective function. So next, constant function. constant function. Constant function. Okay. A function f maps R to R defined as f of x equals to c, fixed number c, for every value of x belongs to domain R, x belongs to R, where c is a constant, where c is a constant, where c is a constant. Then f is called a constant function, a constant function, constant function. So that means, for example, CA, this is set B. For example, say ABC. Here we have 1, 2, 3. For example, A is associated to 2, B is associated to 2, C is also associated to 2. So now, what is the range of this function? Range of this function is equal to 2, only singleton set. If the range of a function is singleton set, that is always constant function. Constant function, understood now? For example, say here you can write f is equal to, we can write like this, a comma 2, b comma 2, and c is also c comma 2. Or clearly we can say that f of x equal to 2 for every x belongs to a. So this is called a constant function. But how many number of constant functions can be defined? That's very important question. So that means actually a is associated to 2, b is associated to 2, c is associated to is only one way. In the similar pattern, these three elements can be associated to 1 also, 3 also. There are 3 ways. That means actually the number of constants from a to b, for example, equal to the number of elements present in the codomain. That's equal to n of b. That we can write it. So very important point. So let us write it now. Number of constant functions from a to b equal to number of elements present in the codomain, n of b, cardinality of b. Okay, next, the f of x is equal to c means f of x we can say y is equal to c. Y is equal to c is represents a straight line and parallel to x-axis. The graph of constant function is always represents a straight line which is always parallel to the x-axis. So that also let us write now that point. The graph of a, the graph of a, but actually the number of constant functions. Okay, and the graph of a constant function, the graph of a constant function is a straight line, is a straight line, is a straight line parallel to x-axis, parallel to x-axis. So this is about the constant function. Okay, right, three constant functions, correct. Next one is identity function. Identity function. Identity function. Identity function. Okay. The function f maps R to R defined as f of x equals to x for every x belongs to domain R is called an identity function. Identity function. Identity function. So example, this is set A, set B. Set A, write down, no problem. 1, 2, 3. Here also 1, 2, 3. F of x is equal to x means f of 1 is equal to 1. 1 is associated to 1 only. 2 is associated to 2 only. 3 is associated to 3 only. This is called identity function IA. Even B to B also, for example. So number of identity functions means only one. That's all. So only one we can define identity function. Identity function is always surjective only. It is one to one, always on to also. Yes, this class is Eamcet only. Right. So now the very important point, the graph of identity function. The graph of identity function means the graph of y is equal to x. The y is equal to x always passes through the origin and makes 45 degrees with x-axis. So now the first point right on here. Number of identity functions. Identity functions from A to A equal to 1. Next important point. The graph of yes, the graph of the identity function, the graph of identity function, the graph of identity function is a straight line passing through the origin, passing through the origin, and inclined at an angle of 45 degrees with x-axis. with x-axis. This is identity function. Okay. Right. Next is equality of functions. Equality of functions. So equality between the functions. When do we say that two functions are equal? So in order to be the two functions are equal, said to be equal, they should have the same domain and they should have the same range. Then the functions are, we say that the two functions are equal. We can say f of x is equal to g of x. For example, f of x and g of x are two functions such that the domain of f is equal to domain of g and the range of f is equal to range of f. Then we say that actually f of x equal to g of x for every x belongs to the respective domain. Okay. Right now, so all into functions are not equal. Right. Two functions, two functions two functions f and g are said to be equal said to be equal said to be equal if providing these conditions. If first point, the domain of f, the domain of f is equal to the domain of g, the domain of g, same domain. Second point, the range of f, the range of f equal to the range of g. Third point, then we say that f of x equal to g of x, both are equal for every x belongs to the domain. We can take examples now. We can consider one example here. Let f maps a to b, sorry, 1 minute. Okay. N to r be defined by f of x is equal to x square and f maps r to r or g maps, sorry, g maps r to r be defined by g of x equals to x square. Now can they be equal? Can they be equal? Can they be equal? See, you check it here. Domain of f is natural number. Here domain of g is real number system. N is the subset of real number system, but domain of f is not same as domain of g. So they are not equal. Therefore, f comma g are not equal functions, are not equal. Yes. So now the special functions let us discuss. That is actually I need to discuss very clearly, but we don't have enough time because this Eamcet class I don't discuss the graphs, but in JE means I discuss very clearly about the graphs of different functions also, how to draw the graphs also. But just I will confine to the concept itself only here. So next function is modulus function. Modulus function. Modulus function. Or we can say that this is absolute value function. Absolute value function. Modulus function or absolute value function. The function f maps R to R, f maps R to R is defined as is defined as f of x equals to mod x equals to x if x is positive greater than 0, 0 if x equals to 0, minus x if x less than 0. So this is the actually definition of the modulus of a function. So once again I request you all, don't chart personal. If you chart personal I will keep id. Okay, defined as like this is called the absolute value function or modulus function. Modulus function. Modulus function. So that means modulus of a real number is always positive. Always positive. Domain means actually real number system. The domain of modulus function is real number system, but it gives us only positive values. 0 to greater than 0 values only it gives. That's why we can write now. So domain equals to domain of this function, set of real numbers, whereas range equals to closed 0 to positive infinity open. So this is the domain and range of the modulus of a function. So some points note down here only, because first point, mod of x plus or minus y is less than or equal to mod x plus mod y. Second point, mod of x plus or minus y, this is greater than mod x minus mod y. This is called triangle inequality also. Okay, right. So let us discuss one more function, very important function, that is greatest integer function. Greatest integer function. greatest integer function. This is called GIF. In so many problems, it will be very useful for even limit chapter, even differentiation chapter or function chapter or integration. Everywhere we can use this chapter. Who is that Racker? All of you just block him. All of you block him. Block him first of all. Useless fellow. So this type of the persons are not useful to our society. Okay. The function f maps R to R. The function f maps R to R is defined as f of x is equal to integral part of x is called the greatest integer function where this is called step function also. Step x is equal to integral part of x, integral part of the number x, or greatest integer not less than x, greatest integer not greater than x, or greatest integer less than or equal to x. Always it will be less than or equal to x. Less than or equal to x. That means integral part of x is less than or equal to x. Always you remember like this. If anybody will come, do like that only. So myself also, if I observe, definitely I will keep them away. We don't want such viewers for us. And one more important point you remember, that's very important point. So here f of x equals to n, that means in the case of n, where n less than or equal to x, x less than n plus 1. N belongs to integers I. Here domain of this function, domain means set of real numbers, but range only it gives us integers I. The domain of the greatest integer function is R, set of real numbers, but range will be we get integers itself only. Understood now? So now the properties. 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 Properties of integral part of x. Let us discuss. Okay. Just block Mr. Trinad also. Suma, block him Trinad. First point. N less than or equal to x, x less than n plus 1. That implies the integral part of x is equal to n. Examples, integral part of 2.5 is there. You can write 2. Integral part of 0.5 is 0. Integral part of minus 1.5 minus 2. You remember like this. So next second one. Always this integral part of x lies between x minus 1 and x itself only. It will be useful for actually squeeze principle also. Squeeze principle also. That means x minus 1 is less than integral part of x less than or equal to x. So next third one. Here integral part of x equal to integral part of x only. Next fourth point. Integral part of n plus x equal to n plus integral part of x. Conditions are provided where n belongs to integer. Where n belongs to integer, then we can write like this. 2.5 is not 3. Yes, 2.5. No, 2 itself only. 2 itself only, not 3 Ashwaradi. No, 2.5 means 2.59999. Only integral part is 2 only. That must be less than xc. Integral part of x is less than x. X is 2.5. 3 is actually more. Understood now? Next, fifth one. This very important point, fifth point I will discuss here. Fifth point is very important. I will write here. Fifth point. This will be useful for problems. Integral part of x plus integral part of minus x equals to 0 if x belongs to integer. X belongs to integer. Equals to minus 1 if x is not a integer. X does not belongs to I. Minus 1.5. Minus 1.5 means the minus 1.5 must be less than 1.5. So minus 1.5 means less than means minus 2 will be less than minus 1.5. Understood now? Even for example minus 2.3 is there. Minus 3 you need to write. Next, fractional